Hey everyone, and this is the Tesla Gigafactory expansion project for economics and finance for engineering projects. My name is Josh. I am a mechanical engineer with a passion for automotives, music, and DJing, pop culture as well.
My name's Tom. I'm studying mechatronics engineering and applied physics. I'm working in the ADF, very interested in autonomous systems.
Tesla is an American multinational automotive company run by Elon Musk, headquartered in Austin, Texas, USA. They design, manufacture, and sell electronic vehicles and battery energy storage devices for use in everything from homes to grid-scale applications. Since 2010, electric vehicles use worldwide has skyrocketed from approximately 20,000 up to 58 million in use around the world in 2024. Unlike other car manufacturers who sell through franchise dealerships, Tesla sells directly to customers. It has created an international network of company-owned showrooms and galleries, mostly in urban centers. Tesla's Gigafactory network is a large-scale manufacturing initiative to produce batteries and electric vehicles globally, with 4 gigafactories located in Nevada, Texas, Berlin, and Shanghai. These plants were designed to use automation and renewable energy to achieve scale and reduce costs. The expansion evaluated here focuses on building additional gigafactory capacity to support Cybertruck and Model Y demand, while increasing supply of stationary battery energy storage systems. The project seeks to improve production efficiency, reduce logistics dependence, and secure battery supply for long-term growth. The proposed Gigafactory expansion will be constructed within the 2025 calendar year, being fully operational and achieving full-scale production by 2026, with an operational lifespan of 25 years.
Tesla currently stands as the 10th largest company in the world with a market cap of approximately 1.5 trillion US dollars, reported by Forbes as of October 30th, 2025. In 2024, they reported 122 billion US dollars in total assets, with outstanding debt around 13.6 billion and a net income of 7.1 billion US dollars. These figures underline Tesla's ability to fund large-scale capital investments and support ambitious growth plans. With strong liquidity and clear profitability, Tesla is well positioned to undertake the proposed Gigafactory expansion without requiring external investors or compromising financial flexibility.
For this expansion, we considered 2 alternative solutions. Alternative A implements full vertical integration by producing 4680 cylindrical cells in-house. This approach requires high automation, robotic assembly, and new production lines, but reduces material use and improves energy density. Alternative A maximizes long-term efficiency with reduced supply chain vulnerability. Alternative B relies on partner suppliers, Panasonic, LG, Chem, and Cattle, to manufacture cells and focuses Tesla's effort on pack assembly and vehicle integration. This cuts initial capital costs but limits long-term cost savings and innovation control. Alternative B allows for quicker deployment but maintains dependency on external supply chain with less robust long-term efficiency.
The Gigafactory expansion represents a major capital investment for Tesla. The initial capital cost covers site construction, automation systems, and renewable energy integration for both alternatives. The ongoing operating costs include things such as energy, labor, and logistics, while maintenance costs sustain high production efficiency within the Gigafactory itself. Although subject to change, the US corporate tax rate is included to provide provided by the US government and IRS for consideration in all estimations and calculations.
For alternative A, the benefits of 4680 cylindrical battery cells include higher energy density, improved thermal performance, and lower cost, largely due to their larger sizes and tabless design. The tabless design significantly reduces internal resistance and improves current flow, allowing for faster charging and discharging speeds, while their larger capacity allows for fewer cells to achieve the same energy output. A major focus on reducing cobalt content in its cathode chemistry, a material that is expensive. This has limited global supply and poses ethical sourcing challenges. In parallel, Tesla's cell architecture redesign, exemplified by the 4680 battery format, allows for fewer parts, simplified assembly, and improved volumetric efficiency. These engineering optimizations reduce the number of manufacturing steps and lower the required capital expenditure per gigawatt hour of capacity. Together, these advancements contribute to a lower cost per kilowatt hour, a critical driver of overall vehicle affordability and profitability. while aligning with Tesla's environmental and ethical sourcing objectives. For alternative B, by integrating proven cell chemistries and formats, Tesla ensures supply stability, consistent performance, and reduced R&D risk, while maintaining flexibility across vehicle and energy storage production lines. Notably, by leveraging established battery formats for the 2170 cylindrical cells, rather than producing all cells in-house, many gigafactory sites concentrate on battery module and pack assembly, incorporating the external supplied cells into Tesla's proprietary pack designs and thermal management systems. This modular manufacturing approach enables faster plant ramp-ups, reduces capital expenditure on upstream cell fabrication equipment, and streamlines logistics across global production sites. The strategy reflects Tesla's focus on operational efficiency and scalability, allowing the company to meet increasing EV demand while continuing to pursue long-term vertical integration in parallel.
Cash flow statements, seen summarized here, cover the project's lifespan, taking into account the time value of money. Cash inflow is the sum total of all incoming money from the project, in this case solely revenue from the sale of final products, both batteries and electric vehicles. Cash outflow is a sum product of all outgoing cash as a result of the project, including initial/ongoing capital investment, operational costs and maintenance costs, and tax payout. Although considered in some later estimations, depreciation of assets is not included as part of the cash flow statement.
Both alternatives are financially viable. BCR is greater than 1 and positive NPV. Alternative A provides higher return on equity and operational efficiency from in-house cell manufacturing. Alternative B offers lower risk and quicker cash recovery, but reduces Tesla's innovation advantage. The net present value represents the difference in discounted projected cash inflow and outflow over the project's 25-year lifespan to provide the present value of the project in the year 2050. The benefit cost ratio quantifies the efficiency of each dollar invested, comparing expected benefits to total costs. A BCR greater than 1.0 suggests a profitable project. BCR is calculated using the formula. Alternative A boasts a BCR of 2.31, meaning for every $1 invested, $2.31 in benefits is expected to present value returns. Alternative B has a BCR of 1.52, indicating a profitable project, but at a lower efficiency.
Here the results of a sensitivity analysis are displayed. Alternative A can be seen to remain viable under all tests. Alternative B, however, approaches dangerously close to becoming unviable with a BCR of 1.25 and 1.37, bordering on the limit of viability for a project of this scale. In both cases, raises in operating costs and capital expenditure have little to no impact on the net present value and benefit to cost ratio of the projects. Overall, Alternative A carries high technological and financial risk, but benefits from Tesla's long-established expertise in automation and supply chain control. These risks are manageable through existing mitigation strategies, procedures, and regulations, supported by contingency allocations of 5 to 10% capital expenditure, which has little to no impact on the project's financial viability, as seen on the previous slide. Alternative B is subject to higher financial and market risk as it relinquishes direct control over cell production costs and timeline. The current volatility of the American market indicates the likelihood of this is very likely. Although technological risks are lower and handled by the supplier, dependency on third-party suppliers raises exposure to supply chain disruptions and price escalation unexpectedly. Mitigation focuses on diversification and long-term contracts with digital oversight to maintain operational continuity. Overall, Alternative A is a less risky project for Tesla due to the internalized nature of the expansion, limiting dependency on external suppliers. This holds true especially due to Tesla's already long proven track record in projects of similar scale and nature.
Alternative A is recommended. Its integrated cell design achieves higher energy density and lower lifestyle costs per kilowatt hour, while Alternative B delivers faster returns. It sacrifices strategic control and technology leadership, proceeding with Alternative A supports a long-term margin growth and reduces supply risk. Further analysis should focus on energy cost reduction through solar integration and battery cycling benefits beyond year 25. Identified weaknesses include uncertainty in future lithium prices and potential changes to EV tax credits. Scenario analysis using discount rates of 8 to 12% is recommended to capture macro risk effects on project evaluation. Thank you so much.